Welcome to Systems of Linear Equations, lesson number 1. We're going to look at solving systems of linear equations by graphing today. And so, although we don't quite know what a systems of equations is, we do know what linear equations are. Linear equations look like y equals mx plus b. They also look like ax plus by plus c equals 0. And so knowing that will help us to compare some equations as well as to set up a system and solve. So in this first exploration, we're going to take a look at what might a systems of equations look like and how do we solve it. And it's not too far off what we have been doing in terms of graphing, but this time we're just going to look for one special thing, and we're going to see that in a minute here. So here's kind of the question or the setup. The Smith family and the Harper family are going to a book fair, and Mr. Smith has 3 adults and 1 child with him, well, assuming he's one of those adults. And for 3 adults and 1 child, they get charged $11 to get into this book fair. And Mrs. Harper, she goes ahead and she pays $12 for 2 adults and 3 children. So based on those 2 sort of values, that 3 adults and 1 child can go for 11 and 2 adults and 3 children can go for 12, we're guessing the price of adults and children are different. And we want to determine what is the cost of an adult ticket and what is the cost of a child's ticket. And so these numbers are small enough, and assuming you're going to estimate what the tickets could be, their prices in terms of dollars, you could probably guess and check your way through trying like $2 or $3 or that type of thing. But we want to just learn what's the basic sort of idea behind a systems of equations and what we're looking for. So whenever we're in a system of equations, we're going to say that we have one variable, or sorry, 2 variables. And so I don't want to always say they're x and y because they're not, but we want to identify what is x and what is y. And so based on how you write this, this kind of relates back to what's independent and what's dependent. But you're allowed to write or choose which variable you want to use for an adult ticket, which variable one used for a child, and actually the solution should be the same. So if we go with x being the adult ticket, y being the child's ticket, we know that Mr. Smith, 3 adults, 1 child for $11. And if we go with Mrs. Harper's situation, 2 adults, because X stands for adults, or the cost of an adult ticket. So 2 times the cost of the adult ticket plus 3 times the cost of the child's ticket equals to $12 total. And so we want to graph these on the grid. And we're going to stay away from technology just for a bit. So I'm going to go back to recording or rewriting here what my 2 equations were, and I'm going to do a little bit of review from last unit where we took a look at writing equations in a form in which we could pull the most information from them and graph them, and that was the slope-intercept form. I'm going to write it on the side here for you. That said, if you write something in the form mx plus b, m will be your slope and b will be your y-intercept. And once you have that, you can start at your y-intercept and you can use the slope to graph. So here, 3x plus y equals 1. Now, it doesn't matter which first step you sort of take algebraically, but the first step has to isolate y, or at least work towards getting x and the number on the same side. So when I'm looking at this, and sorry, that's 11, not 1, 3x plus y equals 11. If I look at this, I'm going to say, well, I already had like a positive y right here. Let's just take x to the other side. Let's isolate y, minus 3x. And so when I subtract 3x from each side, this disappears. Y equals 11 minus 3x, and easily I can switch the order here. Negative 3x plus 11. which tells me my slope is -3 and my y-intercept is 11. So I'm going to go ahead right now and I'm going to actually draw this here. So here's my y-intercept at 11 and slope -3. Okay, that must be like -3 over 1. So I'm going to go down 3 and over 1. I'm just going to put a little dot there. Down 3 over 1 until I can see enough of this that I could maybe take a ruler and draw it. Okay. So there's my first graph. Y-intercept at 11, slope of -3. I'm going to do the exact same thing here. I have a little bit of an extra step though because it's not 1y. So I'm going to do the exact same thing. I'm going to take away the 2x on each side. Oops, I can't cancel over here. That was -2x plus 12 is left. So sort of ignore my scribbles there. And that's equal to 3y. And you can see already I've automatically just wrote x in front instead of showing you the subtraction and then switching. So I've just gone right ahead and wrote x in front so that it looks like mx plus b. And I might be tricked here to say slope is -2 and y-intercept is 12. It's not, because I have to divide by that 3. So when I do divide by the 3, -2 divide by 3, x, 12 divided by 3 is +4. And so my slope is -2/3 and my y-intercept at +4. And so treating slope as rise over run, down 2 over 3. Let's start at +4, our y-intercept, down 2 over 3, down 2 over 3. And now I have about 3 points on the graph. I'm going to use my ruler to connect the dots. Okay, so I'm going here, and I'm going here. And so something interesting happens right here. The graphs actually intersect. And if I'm looking for the coordinates where they intersect, I can see they intersect at x3, y2, so I'm going 3, 2. And so when I'm thinking about this system, I want to know sort of what that represents. So I'm going to just rewrite it down here. They intersect at 3, 2, and this was x and y. Way up top here, I said x is going to be the entry fee for an adult. So giving a little bit of context to that, x must be $3. I can put that in writing as the cost of an adult ticket is $3. And so when I say y at 2, and go ahead and say, well, why was the cost of a child ticket? I said that before I even started the problem. That's how I wrote my equations. The cost of a child is $2. And so this would be, or this whole thing, both graphs would form a system of equations, and the solution to the system where those equations are equal would be 3, 2, and I would state this as an ordered pair and in words. Okay. So on the back here, oh, here's the right page. This one should look like yours. It says here, okay, so here's a system of equations. It says we looked at 2 equations on the previous page, and so there are many values of x and y which satisfy each of these equations individually. That's why we can graph those lines and get the ordered pairs. But however, if we consider both of these equations at the same time, there's only one solution that they have in common, and that solution is x3, y2, or 3, 2. And so when they're considered at the same time, we say we have a system of equations in which the solution would be an x and a y value that satisfies each. And so I almost want to replace this has to satisfy both. Both equations in the systems, x and y, need to be able to plug in, and left side equals right side. And so if that's true, where is the first equation equal to the second equation? That's like asking, where does the first graph meet the second graph? So when you're looking graphically, the solution is the point of intersection. Okay, so in terms of the next problem, class example number 1, a system of equations is represented on the grid. How do I know that? This graph would represent one equation, this graph would represent another. And so we're saying, what is the solution to that system? It says an integral solution. That means integer. So you don't have to worry about decimals or fractions or anything. You're just going to choose the integers it's closest to. It says state the solution. Now, there's a number of x and y values that would fit on this graph and a number of x and y values on this graph, but what do they have in common? They share one point. They have that in common. That will be our solution. This looks like it's about 2, -1. So I'm going to write x is 2, y equals -1. That means my ordered pair, 2, -1. That's my solution to my system of equations. Okay. Here's another one for us. Graph the system of equations without using technology. 2x plus y equals 2. X minus 3y equals 15. Again, I'm back to the point where I can't graph anything unless it's in the form y equals mx plus b. So I'm going to go to that form first, and then I'm going to graph them and look at that, and then on the next page we get to use our calculator. So always, I like to rewrite my two equations, and graphing without technology requires a few pieces of information. Because I don't feel like going through both of these and finding x and y intercepts or anything like that, I'm going to go to slope intercept form because that's the easiest for me to visualize where this graph starts and where it's going. So again, y needs to be isolated from x in the number. That's this mx plus b form. So I'm going to leave y here, take away the 2x on both sides so that I can say y is alone. And then on this side, now I have a -2x and a +2. And over here, I might want to either take the x, or I'm going to show you another method here. What if you moved y? Maybe you just decided you like to move y better, you want to go to the right. Let's move 3y and see what happens. We see x, that's gone, equals 2, 15 plus 3y. Now I'm not done because this is y with a number, and I want x with the number. So actually I'm going to just take the number over. I'm going to subtract 15. X minus 15 is 3y. And so I can go here and divide by 3 on both sides. Y equals, I'm going to imagine there's a 1 here. 1/3 x, I'm starting to squish. -15 divided by 3. Oops, -5. I'm going to write that neatly for you here, just down here. 1/3 x minus 5 equals y. So I go back to both of these. They're both in y equals mx plus b form now. This one tells me start at +2 y-intercept, right here. Go, or have a -2 slope, which means down 2 over 1, if you want to picture it like that. Slope is -2 over 1. Y-intercept +2, so I'm going to go over here, down 2 over 1, down 2 over 1. Once I have about 3 points, I feel confident enough to draw a line through the 3 points to continue my graph. And so there are some limitations to drawing. Sometimes you might just look like they're just a little smidge off, but that's okay because we are going to assume that these are integers. Okay, 1/3 x minus 5. That tells me slope 1/3, y-intercept -5. I'm going to start at -5. I'm going to go rise 1, run 3, up 1 over 3. There's my solution. Up 1 over 3, so I have enough to draw the second graph. And so I can see here is my solution. Here's my system, 2 graphs. Here's the solution where the point that they share, an x, y that would belong to both equations. State the solution. That is at +3 on the x-axis, -4 on the y-axis, 3, -4. Now it says verify by replacing both values in the original equations. This is what makes a solution to a system. We said this x and this y, where x is 3, y is -4. This has to fit and work for both equations. Back to my original equations that says 2x plus y equals 2. I just want to do a quick check. Is it true that if I sub in x and y here, 2x is 3 plus y is -4, is that going to equal 2? Well, this is 6 plus -4. That's 2. And so 2 equals 2, I can say left side equals right side. I verified that this is a solution for the first equation. In other words, it's a point on the line. And secondly, I'm going to go back to x minus 3y and verify if that equals 15. And so when I sub in x3, y -4, I'm just verifying, does that equal 15? And so I see -3 times -4 is 12. That double negative makes positive. 3 plus 12 is 15, and so I've gone all the way through this and say 15 is 15, left side equals right side. And so I verified it for both equations. I've algebraically verified that it's a solution. All right. Okay, now for the more fun stuff, maybe. You can do this on your calculator. However, this first step we've been doing where we go at y equals mx plus b, still valid. So we see a system of equations. Sometimes we write them vertically over top of one another. So we say 3x plus y equals 11, 2x plus 3y equals 12. We know already this is our Mr. Smith and Harper family at the book fair type equations. So we want to solve this on the graphing calculator. So I'm just going to pull up actually the work that I did back when I wrote these in y equals mx plus b form algebraically. I'm just going to copy down my final forms for both of those. I had y equals -3x plus 11 and y equals -2/3 x plus 4. So that was off the front page of this lesson. And so now I have a way of using my graphing calculator to find the solution. And we've said the solution is the intersection. I have a way of finding the intersection on my calculator. So I have 2 equations for y. I can take my pick. One of them needs to go into y1. One of them needs to go into y2. Doesn't matter which one. But I'm going to label y1 as the -3x plus 11 and y2 as the -2/3 x plus 4. So I'm going to enter y1, have -3x plus 11. And I'm going to go down here, y2, -2/3 x plus 4. And I'm just going to verify that that matches what I had. It does. Okay, going to graph, and so I might have to change my window if I can't see my solution. But I can. It's right there. If I want to know on the calculator what that point at intersection is, I go to my trace menu, second trace gives me the calc menu. Go down to number 5. I want to know where they intersect. This is the one of the easiest analysis tools because we just go enter, enter, enter until it says intersection x is 3, y is 2. So I'm going to go down here, x is 3, y is 2. And so it asks me here, can you state a suitable window? And so this is a little bit open to variation. The one that would show the point of intersection, I'm just going to write that standard window that said x from -10 to 10 going up by 1, y the same, the 10 by 10 standard window that my calculator is on. And so it's not going to show both y-intercepts, but what it should show is the intersection, and that's the main piece of this. Okay, let's try class example number 4. I'm going to flip on the back, and so you can see I'm kind of skipping over the directions because I'm trying to show you on my calculator what it looks like rather than reading through the instructions. So here's my last example. Solve the following system of equations using a graphing calculator. It says 6a plus 7b equals 5, 3a equals 14b. And so looking at this, a and b, now my calculator doesn't graph in terms of a and b, but it does graph in terms of x and y. So I'm just going to say let x be a, y be b. I'm just going to replace a with x in that equation, and I'm going to replace b with y, and in the second equation as well. Oh, that's a y, not b. There we go. And so it says, can you figure out the solution and list the answers as exact values? Okay, so that's probably going to mean they're going to be fractions. But I have a way my calculator can find me fractions, lucky that way, and a quick sketch up here in the corner. So would love to go ahead and graph these. However, y is not alone, and in order to enter it in y equals, it needs to be isolated. So I'm just going to rewrite, I'm going to go down here where it says algebraically verify and sort of copy down my two equations so that I can work with them. Hard to see there. There we go. So this one, easy to get y alone. It's just 14 times y. I'm just going to divide by 14. So 3 over 14x equals to 14 divided by 14, 1y. And I would graph that in y1 just because it's the first equation I solved. I'm going to go over here, and I want to get x and the number together, y on the other side. So I'm going to take away the 6x so that I have 7y equals 2, and I'm just going to write by convention the x in front, -6x plus 5. One extra step to get 1y, divide everything by 7. 1y equals to -6 over 7x plus 5 over 7. So lots of fractions even in my equations. Got this as y equals, I'm going to enter it in y2. So I'm going to bring up my calculator again. And I got to clear the graphs I had in there previously. So y1, 3 over 14x. Okay, I get in the habit of doing brackets on that because I want to control the 3 over 14 times x. I don't want it to go 3 and then divide by 14x. So same thing over here. When I enter y2, I'm going to go bracket -6 over 7x plus 5 over 7. Graph. See if I can see where they meet. Looks like right here, almost pretty close to the origin there. I want to know what the coordinates are, so I go second calc. Where do they meet? Where do they intersect? That's number 5 for the shortcut. Enter, enter, enter. Intersection, all in decimals. Let's write down what I have first. X equals 0.666 repeating 6666, let's go 66667, y equals 0.142857. And so this is true that this is your solution, but we want to write these as fractions. I'm just going to show you how to sort of copy out of this, how to get your x and your y in fractions without trying to guess. And so I'm just going to quit the graphing mode. I'm going to go back to this, or sort of just my calculator mode. I'm going to push the button X because by performing that intersection, getting that number, I've stored it. I'm just going to say X equals, it copies it down, 0.6 repeating. Then I'm going to hit math fraction. And it says 2/3. So this is equivalent to 2/3. And so I believe there's a way to do the same with y. Let's see if we can find that way. If we use, you know what, let's use just the x we have. Because if I have x, I can go ahead and, oh, hey, look, hey, there's instructions up here. Hit alpha 1, enter. Can we do that? Alpha, oh, there's y. See it in the green next to number 1, alpha, there we go. Alpha 1, it's stored by your intersection. Enter, there's my fraction, math, fraction, 1/7. Well, that's handy. I'm learning something new. Okay, so x 2/3, y 1/7. You'd write that as a ordered pair, 2/3, 1/7, or state both of them. They have to both be there for the solution. Algebraically verify, go ahead, the same way I did on the other page, didn't verify that left side equals right side, but it will. So the only thing I'm going to add here is a quick sketch, just the best I can. So a very kind of shallow slope line there, and my second line kind of coming through here. Good enough for me. There's my point, there's my solution. Okay, so let's go through and assign or complete our assignment. Take a look on the Google Classroom for a list of the questions that I want you to complete. Short 3-page assignment. You can go there now and start to practice.